Okay, who remembers what's the difference between CRC and Hamming distance? What's Hamming distance? What's CRC?
Detection of an error.
Error detection, algorithm. Which one is an error detection and correction?
CRC. No. Hamming distance.
Hamming distance. CRC is what?
That's a detection.
Error detection. Why? That's why they use it. Where? Where is it more used? CRC.
Or like any.
Internet. What was it? What did we say that?
CRC.
Where I have two copies. Usually I have it in communication. Communication. Where I have communication. Client server. Peers. I'm sending you a copy of what I have. If it gets lost or if it gets damaged on the way, what happens? You drop it, you send me a knack, there was something wrong, resend the previous packet. That's CRC, error detection. It detects it, but it doesn't correct it. Hamming distance, it's an error detection and correction. So where will it be more suitable, or where will it be used more? We said what? Where you have one copy. One copy of what? Data. Hard disk, memory, hard drive. Those they use Hamming distance. Let's say I have a message M. And how many bits you want it? 9? Here's a 9-bit message. What's the first step in Hamming distance? What do we need to do? What do we need to do in Hamming distance? Find what? R. What's R? The redundant bit, or the bits we're gonna append to the message. How do I find R? M plus R plus 1 is going to be what? Less or equal 2 to the power R. And sometimes they call R syndrome. You might find it in other books called syndrome. M is 9-bit. What is R? What should we start with? 1 plus 1, is it less or equal to the power 1? No, so what would I do? I'll use R as 2. 2 to the power 1. What will this give me? 12, is it less or equal 4? No, I'll use R as 3. Is it less 13, less or equal 8? No. So I'll use R as 4. Now how much do I have? 14. Is it less or equal 16? So here the condition is true. So R equals what? 4. So now I know I'm going to add
9 plus
4 bits. My encoded word, which is message M plus R, is going to be 9 plus 4. 13 bit. 13 bit. So now it's really important. Sorry guys, I'm not moving, I'm recording it so you can. Anybody needs this? So now what do we do? What's the next step? We got R. What do we do?
From 1 to 13.
From 0 or 1?
1.
1. Eight. 12, 13. What are those? Those are going to be my message
Yeah.
and 13 bits. But in CRC, what did we do? Where did we append the extra bits?
At the last. The key minus one.
At the end. What's the disadvantage of that? Can I append? Can I do it here? Can I put the 9 bits of the message and the 4? Why I can't do that?
Need to have perfect square.
What?
Perfect square.
What is that?
6 square beats.
Square bits. Perfect square is
1,
like 2 raised to
2,
3.
4, and 8.
Yeah, why is that? Why we didn't append them at the end and made it easier? As in, this is going to be extra processing time for the computer to calculate which bits. This is going to be an algorithm. It's going to be either a software or a hardware. So why not append it at the end or at the beginning?
So if you detect which bits are missing, well,
How's that?
if it's all at the beginning, if you lose all of those,
That's why if I had, where do we use this? We use it in hard disk, CDs, DVDs, where I have one copy. So think of a DVD now. If it's scratched from one place, does that mean that's it? The DVD is ruined?
no.
But what if the 4-bit we added was here? Can we get the data back? No, if they were this, it's a scratch. Was the 4 bits? We can't get it. So when we spread them between the other bits, the message bit, and this they use it in security. They call it diffusion. So it'll be harder for hackers to guess which bits are the original message and which bits are the encryption. So how do I pick the R bits, the redundant bits?
1, 2, 4, 8.
I have to what? Factorize to power of what?
0.
2's.
To the power 1. 0 plus 1.
Power 2, 2 to the power 1. Let's see. 0 and 1. Power 2, that's all right. 8 and 4. Yeah. Now I need 4 bits. Just 4 bits as redundant bits. So which bits will be my redundant bit? I take what?
1, 2, 4, 8.
All powers of one factor.
What?
Is it just the powers of one factor?
Oh, the powers of one factor. Well, I have what? 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. That's now should make it easier. So now if I gave you 10 bits, how many bits do you think the redundant bits are going to be? Without doing the equation.
Same amount.
4. When will it be more?
17 or after 17, yeah, after 16.
After 12. Why 12? 12 plus 4 is 16. And bit 16 is going to be what? 2 to the power 4, it's going to be a redundant bit. The 5th one. And when is the one after that? 32. So those are my redundant bit. So let's put the message now, and then we can calculate. How do I calculate the redundant bit? What's that? We pick, we can If I didn't tell you what it is, you can pick either. But you have to tell me that you picked like odd or even parity. What do I mean by odd and even parity? Let's say we had 7 bits. 7 bits. They used to add a parity bit. What was a parity bit? It was the number of ones. How many ones do I have here? 1, 2, 3, 4, 5, 6. And it's, be careful, parity bit is the number of ones including, so this is 0 if it was even parity. If it was odd, what will it be? 1 to make it 7, including the parity bit. So what are my bits here? How do I know which ones I'm going to calculate the parity? Wherever I have a 2 to the power 0, I count the ones in those. Do I have a 1 here? Do I have a 1 here? No. So here I have 1, 2, 3. And which parity do we want to use? Odd or even? Odd, this will be 0 because I had 3 bits. Now 2 to the power 1. The next one, I go pick every number that has a 2 to the power 1. Just those. 0, 1, 2, 3, 4. I have 4 ones and I have what? And I'm using odd. So I'll add a 1 to make it 5, to make it odd. Now let's take 2 to the power 2. I'm gonna have this one. So 1, 2, 3. So it will be what? 0. And last 1. I'll take what? 2 to the power 3's. And it's going to be all of those. And I had 3, it's going to be what? 0. This will be my message with the redundant bit. And they call it what? Encoded word. Encoded word. So if I say they use it in memory, in CDs, in DVDs, in hard disk, how do they use it? How do they implement it? What do you think? Everything saved has to be saved this way. Anything you save it on a DVD has to be what? Using hamming distance. So you can apply it. You can't say, oh, I'm going to apply it after you lose the data. Be careful. What if we had an error? We said this is an error detection and correction. So it will correct an error. Let's see how it will correct it. Let's say I had a 1 here. What will happen? Is this gonna change? 2 to the power 0, is it gonna change?
No.
So it's 0. 2 to the power 1, is it gonna change?
No. 2 to the power 2,
2 to the power 2. Let's calculate the parity for this now. 1, 2, 3,
Four, actually.
and 4.
So we.
So it should be
One.
1. So this should trigger something is going on in this bit.
2 to the power 2 is equal to 1.
What do I have? 1, 2, 3, 4, 5.
But it's 4.
Oh, 4. Sorry. Yeah. Alright.
Should be 1.
4 should be 1. This should trigger something is wrong here. So what do we do? What's this number? What's bit number? 4. And this is?
8. Which is 12.
And I add them. Equals 12. I go to bit 12
Change.
and change it. The correction of it is easy, yeah? Any problems with this? Good? Now you said both are good.